Our universe is a place of constant motion. From the moment of the Big Bang, everything has been in a state of perpetual movement. Stars are born, live out their lives and die, often in spectacular supernovae. Planets orbit their stars, moons orbit their planets, and even entire galaxies are on the move. From the smallest particles to the largest galaxies, everything is in a state of flux. On a microscopic level, atoms and subatomic particles are in constant motion, vibrating and interacting in ways that are still not fully understood. On a macroscopic scale, galaxies spin and dance through the cosmos, influenced by the gravitational pull of dark matter and the mysterious force of dark energy. One of the most remarkable discoveries of the 20th century was that the universe itself is expanding. This revelation came from the meticulous observations of astronomers like Edwin Hubble, who noticed that distant galaxies were moving away from us. This wasn't just a random occurrence, it was a pattern that suggested a dynamic, ever-changing universe. This expansion isn't like an explosion, with everything flying outward from a central point. Instead, it's more akin to a balloon being inflated. As the balloon expands, every point on its surface moves away from every other point. Similarly, in our universe, galaxies are moving away from each other as the fabric of space-time itself stretches. Instead, it's as if the very fabric of space-time is stretching, carrying galaxies along with it. This concept can be difficult to visualize, but imagine a grid that represents space-time. As the grid stretches, the points on the grid, which represent galaxies, move farther apart. This stretching of space-time is a fundamental aspect of our universe's expansion. The driving force behind this cosmic expansion is a mysterious force called dark energy. Dark energy makes up about 68% of the universe, yet we know very little about it. It's an enigmatic force that seems to counteract gravity, pushing galaxies apart and accelerating the expansion of the universe. We don't fully understand dark energy yet, but we know it acts as a sort of anti-gravity, pushing things apart rather than pulling them together. This discovery has profound implications for our understanding of the cosmos and the ultimate fate of the universe. If dark energy continues to dominate, it could lead to a future where galaxies are so far apart that they become isolated islands in an ever-expanding void. The more the universe expands, the more dark energy seems to dominate, leading to an accelerated expansion. This means that not only is the universe getting bigger, but it's doing so at an ever-increasing rate. This accelerated expansion was a surprising discovery that has challenged our understanding of cosmology and the fundamental forces at play in the universe. This accelerating expansion has profound implications for the future of the universe and our ability to explore it. As galaxies move farther apart, the distances between them become so vast that it may become increasingly difficult, if not impossible, for future civilizations to travel between them. The universe could become a much lonelier place. As the universe expands, the distance between galaxies increases. This means that the light from distant galaxies takes longer to reach us. And over time, some galaxies may become so distant that their light will never reach us at all. This has significant implications for our ability to study the cosmos and understand its history. The farther away a galaxy is from us, the faster it appears to be moving away. This phenomenon is known as redshift, where the light from distant galaxies is stretched to longer, redder wavelengths as they move away from us. Redshift is a key piece of evidence for the expanding universe and helps astronomers measure the rate of expansion. This relationship between distance and speed is governed by Hubble's law, a cornerstone of modern cosmology. Hubble's law states that the farther away a galaxy is, the faster it is receding from us. This law has been instrumental in helping scientists understand the scale and structure of the universe. The expansion of the universe is not just a theoretical concept, it's supported by a wealth of observational evidence, including the redshift of light from distant galaxies. These observations have been made using some of the most advanced telescopes and instruments available, providing a window into the distant past and the dynamic nature of the cosmos. This redshift is similar to the Doppler effect we experience with sound waves, where the pitch of a siren changes as it moves towards or away from us. Just as the sound waves are compressed or stretched, the light waves from galaxies are stretched as they move away, shifting them to the red end of the spectrum. This continuous expansion is a fundamental property of our universe, and it plays a crucial role in shaping its destiny. As we continue to study the cosmos, we gain a deeper understanding of the forces that drive this expansion and the ultimate fate that awaits our ever-expanding universe. The journey of discovery is far from over, and each new observation brings us closer to unraveling the mysteries of the cosmos. The expansion of the universe leads to a fascinating concept, the cosmic horizon. This boundary, though invisible, marks the edge of the observable universe, a limit defined not by physical barriers but by the very fabric of space and time itself. Imagine shining a beam of light into the vastness of space. This light, traveling at the ultimate speed limit of the universe, embarks on a journey through the cosmos, illuminating the darkness as it goes. That light travels at an incredible speed, approximately 299,792,458 meters per second. This speed, known as the speed of light, is the fastest anything can travel in our universe. However, even at this breakneck pace, there's a limit to how far light can travel in the age of the universe. This limit is determined by the age of the universe and the rate at which it is expanding. This limit is the cosmic horizon. It represents the maximum distance from which light emitted since the Big Bang could have traveled to an observer on Earth. The cosmic horizon is not a physical boundary like the surface of the Earth. Instead, it's a boundary in time, representing the farthest distance that light has had time to travel to us since the Big Bang. Instead, it's a boundary in time, representing the farthest distance that light has had time to travel to us since the Big Bang. This means that the observable universe is essentially a sphere centered on the observer, with a radius defined by the cosmic horizon. Anything beyond the cosmic horizon is currently invisible to us because the light from those distant regions hasn't had enough time to reach us yet. These regions remain shrouded in mystery, beyond the reach of our telescopes and instruments. The existence of the cosmic horizon has profound implications for our understanding of the universe. It means that the universe we can observe is finite, even if the universe as a whole might be infinite. It means that the universe we can observe is finite, even if the universe as a whole might be infinite. This finite, observable universe is a small fraction of the entire cosmos, limited by the speed of light and the age of the universe. Furthermore, the accelerating expansion of the universe means that the cosmic horizon is constantly moving outward. As the universe expands, more regions of space come into view, but at the same time, some regions move beyond our reach. However, objects beyond a certain distance are receding from us faster than the speed of light, making them permanently unreachable. This phenomenon is a result of the universe's expansion, which stretches the fabric of space itself. This means that a significant portion of the universe, estimated to be around 94%, is already beyond our reach. These regions will never be observable, no matter how advanced our technology becomes. As time goes on, more and more galaxies will cross this cosmic horizon and disappear from our view forever. The universe we can observe will continue to shrink, leaving us with an ever-diminishing glimpse of the cosmos. To understand the structure of the universe on the grandest scales, we need to rewind the cosmic clock to a fraction of a second after the Big Bang. This is a time when the universe was incredibly hot and dense, a primordial soup of particles and energy. The conditions were so extreme that the laws of physics as we know them were in a state of flux, and the universe was a chaotic, rapidly changing environment. During this incredibly brief period, the universe underwent an exponential expansion known as cosmic inflation. Imagine the universe as a tiny, compact balloon that suddenly inflates to an enormous size in a fraction of a second. This rapid expansion stretched the fabric of space-time itself, smoothing out any irregularities and setting the stage for the universe we observe today. This period of rapid expansion, driven by a hypothetical field called the inflaton field, lasted for only a tiny fraction of a second, but had a profound impact on the evolution of the universe. The inflaton field is a concept in theoretical physics that helps explain how this rapid expansion could occur. It's a field that permeates all of space and has the unique property of causing repulsive gravity, which drives the exponential expansion. Cosmic inflation explains several observed features of the universe that were difficult to account for with the standard Big Bang model alone. For instance, it addresses the horizon problem, which questions why regions of the universe that are far apart have nearly the same temperature and density despite not having had enough time to exchange information or energy. For example, it explains why the universe appears remarkably uniform on large scales with a nearly homogeneous temperature and distribution of matter. This uniformity is a direct consequence of the rapid expansion during inflation, which smoothed out any initial irregularities and created a consistent, even distribution of energy and matter across vast distances. Inflation also explains the origin of the tiny fluctuations in the density of the early universe, which later grew under the influence of gravity to form the galaxies and galaxy clusters we see today. These fluctuations were quantum in nature, arising from the random microscopic variations in the inflaton field. As the universe expanded, these tiny quantum fluctuations were stretched to macroscopic scales, seeding the large-scale structure of the cosmos. The concept of cosmic inflation, while still a theory, has gained significant support in recent years due to observations of the cosmic microwave background radiation, the faint afterglow of the Big Bang. This radiation provides a snapshot of the universe when it was just 380,000 years old, and its detailed study has revealed patterns that are consistent with the predictions made by the inflationary model. These observations have revealed subtle patterns in the temperature and polarization of this radiation that align with the predictions of inflation. The tiny variations in temperature and polarization are the imprints of the quantum fluctuations from the inflationary period, providing a direct link to the universe's earliest moments. Cosmic inflation, therefore, provides a crucial piece of the puzzle in our understanding of the universe's earliest moments and its subsequent evolution. It not only explains the large-scale structure and uniformity of the cosmos, but also offers insights into the fundamental physics that governed the universe's birth and rapid growth. As we continue to study the cosmos, the theory of inflation remains a cornerstone in our quest to unravel the mysteries of the universe. Galaxies are not randomly scattered throughout the universe. Instead, they tend to clump together in groups and clusters, much like islands scattered across a vast cosmic ocean. Our own galaxy, the Milky Way, is part of a small group of galaxies called the Local Group. The Local Group contains about 54 galaxies, most of which are dwarf galaxies, much smaller than our own. The Milky Way and the Andromeda galaxy are the two largest members of the Local Group, and they are gravitationally bound to each other, destined to collide in the distant future. The Local Group itself is part of an even larger structure called the Laniakea Supercluster, a massive collection of galaxy groups and clusters spanning hundreds of millions of light-years across. These galaxy groups and superclusters are interconnected by a vast network of filaments and sheets of dark matter, forming a cosmic web that stretches across the observable universe. Gravity plays a crucial role in holding these structures together, counteracting the expansion of the universe on these smaller scales. However, the space between superclusters is still expanding, making it increasingly difficult for us to reach even our nearest galactic neighbors. In the vast expanse of space, galaxies are not stationary objects. They move and interact with each other under the influence of gravity. The Milky Way, our home galaxy, is currently on a collision course with our nearest large galactic neighbor, the Andromeda galaxy. This colossal cosmic event is predicted to occur in about 4.5 billion years. While the thought of a galactic collision might sound catastrophic, it's important to remember that galaxies are mostly empty space. The stars within each galaxy are so far apart that it's unlikely that any two stars would directly collide during the merger. However, the gravitational interaction between the two galaxies will have a profound impact on their structures. As the Milky Way and Andromeda galaxies approach each other, their gravitational pull will distort their shapes, drawing out long streams of stars and gas. Over millions of years, the two galaxies will pass through each other multiple times, creating spectacular displays of star formation as gas clouds collide and ignite. Eventually, the two galaxies will merge completely, forming a single giant elliptical galaxy. This new galaxy, sometimes nicknamed Milkdromeda, will be a completely different place than the two spiral galaxies that preceded it.